Perfect answer. Exactly right. This reaction is going to happen quickly because there's lots of things bouncing around, and as the things bounce into each other, they are going to strike one another, and that allows the reaction to happen. Whereas here, it's going to be tricky for them to find each other. And for most things, this is indeed exactly how it works. Now, today, we're going to learn about how we can do calculations with that. All right? So we are going to learn the equations that govern how fast a reaction happens. So get this note out, follow along, because this guy is a really key concept. We're going to relate to this as we get into next unit. So, today's lesson 3.8, the rate constant and rate laws. And this is straight, grade 9 math. Table of values, find the rate of change, talk about it.
I don't like grade 9 math.
So look here. I want to note something. What we said yesterday was that if I change how much stuff I have, it should change how fast the reaction happens. Does that make sense? Now, sometimes it won't. In fact, there are some reactions that we call zero-order reactions. We'll talk about what that means. But what I want to note here is, let's learn how we read this table. Here, I'm setting the initial concentration. And we're going to track the initial rate. Of the reaction. We're going to set the initial concentration, and we're going to track the initial rate. So in the first trial I did here, what did I decide to set my concentration of A as? 0.1 molar, which means 0.1 moles in a liter.
Molar?
Yeah. Molar means moles per liter, another way of saying it. And, no worries, what was the rate of the reaction when I did that?
15 molar per minute.
0.15 molar per minute. Then, in this case, I said, okay, let's see what happens if I take the concentration and if I double it. We're going to double the concentration of A. And when I doubled the concentration of A, what happened?
Nothing. They all look the same. The rate stayed the same because in a zero-order reaction doesn't change the rate.
Very good. A zero-order reaction is a kind of reaction that doesn't depend on how much stuff you have. There aren't many things that are zero-order reactions, but these would be reactions where the molecule A doesn't have to interact with anything else. It doesn't have to bump into B. It doesn't have to bump into a catalyst. If it just depends on itself, decomposition reactions tend to be zero order. They don't have to bump into each other to decompose. You just get them hot enough and they decompose. So in a zero order reaction, we say the rate is constant. For zero order, these are reactions where at a given temperature and pressure, the rate of the reaction doesn't change. It's some constant K.
Like acceleration of kinetics.
Very good. And if you note here, finding K is super easy. What is K for this reaction at this temperature and pressure? 0.15. No matter what, at this temperature and pressure, the reaction rate is 0.15, 0.15, 0.15. Now again, K order or zero order reactions are pretty specific. The least common one we're going to deal with. But for zero order reactions, we start with the easiest example. The rate is just constant and it will just happen at the rate it happens. The other place you see zero order reactions is with really slow acting enzymes, where finding a substrate basically doesn't matter because that happens fairly quickly and then the enzyme takes its sweet time doing what it's doing. In that case, the step where it has to find another molecule basically doesn't matter. And so we call that a zero order reaction. That's the most common example I can think of, actually. My phone just went off for some reason. My neighbor came to my house last night. We share a hedge in our backyard, and he said, "Oh, hey, the guy's coming tomorrow to tear the hedges out." And the hedges are on my property, not his. And so I thought, do I want to make a big deal of this? And then I thought, I have a fire pit in my backyard that isn't at all up to code because it's too close to a tree and a building. So I said, sure, sounds good. Have fun. Let me know if you need any tools. So it's down, and my wife says it looks nice. Anyway, he's putting a fence in, so hopefully it's a nice fence. We'll see, because that's pretty presumptuous, just be like, hey, I think he may have spoken to me about it like in passing once, but anyway. So, because I've got my illegal fire pit, and I'm planning to build a workshop in my backyard that I'm going to pretend is a garage, but really is going to be a workshop, I just want to keep this guy happy. Why am I recording this? Anyway, that's what these texts are about. They're about my illegal shop. All right. Raiden, I'll be with you in just a minute when these guys get doing some math, and I'll help you out if you need it. Thank you. Sorry, I don't know why that's so loud. Yeah, sorry.
I can just hear the hiss.
The hiss? Yeah. Okay, you know what's driving me nuts? Do I think we should offer them money for the fence?
No.
No, he didn't ask me in advance. Oh, I guess we should. I think you have to offer
him a cold beverage.
No, I think you have to offer, and then he'll say no. I think that's the manners of this
What
thing.
if you offer and he says yes?
Is that you say, do you want us to take care of half the cost of the fence? And if he should say, no, it's my fence, I'm building. I don't know why he's Southern now. He'll be like, I don't know why, but it's my fence.
He says yes.
Well, then I'd give him the money, I guess.
He sulks for 3 nights.
I don't sulk. Sometimes I sulk. Okay. Now, on the other hand, a very common type of reaction is what we call a first order reaction. And in a first order reaction, we start with the same thing. So we set the concentration, and again, this time I just pick a random concentration. In this case, I set it at 0.1 molar. And what was the initial rate?
Everything is doubled.
Very good. But this time, and listen, I want to explain, these are all separate experiments. Does that make sense? Look, I want to make sure you're really understanding what we're doing here. This would be like the first time I went and did this experiment. I got my A, and I diluted it, so it was 0.1, and then I start the reaction, and I measure the rate. Does that make sense? Then this time, whole new reaction. I wash all my glassware, new glassware. I repeat the steps, only this time, instead of starting with 0.1, I'm starting with 0.2. Does that make sense? We're not talking about the same experiment as it keeps going. We're talking about stopping, cleaning up, resetting, trying again, but this time with a different concentration. Right. And when I doubled the concentration of A here, what happened to the rate of the reaction? It doubled. The rate is how fast the reaction goes. So you can measure.
0.3 moles per minute.
It means that every minute the concentration's dropping by 0.3 molar per minute. Now, can that even happen for a whole minute? No, because I'm only starting with 0.2 molar. That's okay. This is a reaction that happens pretty quickly. It's over pretty quickly. Imagine like baking soda and vinegar. Vinegar. Baking soda and vinegar.
Soda?
You heard me. And what happened when what did I do to the concentration here? Yeah, I quadrupled it. And what happened to the rate when I quadrupled it? Very good. So in a first order reaction, however I multiply the concentration, the rate is multiplied by the same number.
So then your acceleration would be.
Orlando, I think you still need to move to the left.
I'm sorry. Is that better? Good. You meant me physically, not the page, right? Okay,
And
good.
why do you just try and stretch your head around him instead of move?
You can always ask me to move. Just tell me. Be like, hey, Orlando, your fat head's in the way. I mean, don't say that. That'd be rude, but you get the idea. Okay, so
So Mr. Orlando, would the acceleration be instead of constant would be rising?
yeah, now we're not talking acceleration, though we are. But in this case, this would be, if we looked at yesterday, concentration over time, this would be a graph like we had yesterday, where the rate is changing based on the concentration. Higher concentration, higher rate. So now, with that in mind, what would the equation here be? Rate, in this case, isn't constant. Rate is linear. And we know how to do a linear equation. It would be mx plus b, right? But in this case, could we have a y-intercept? Is the reaction going to stop if we still have stuff left? No. So it's a direct linear relationship. So it's mx. Now in this case, in science for constants, we like to use k. And in this case, what is our x value? Yeah, the concentration of A. So it's linear. You're exactly right. This is a linear relationship.
Would it be linear or would it be exponential? Or is it just linear? Oh no,
And the nice thing is, say we wanted to solve for k, what could we do? We could just take any place on the table of values and we could substitute them in. We could take this run, and here we could say what? What is the rate in the one I've highlighted yellow? 0.15 molar per minute equals k times, and what do we have over here? 0.1, and what's the unit on that? Molar. Shh, guys, I want your focus up here, okay? And how would I solve for k here? Yeah, I just divide both sides by 0.1 molar. And I would get, in this case, k equal to, can anyone do that on the calculator? Can you double check I did that right? Sometimes I get the decimal stuff wrong in my head. Dividing by, you got hands, thank you. And if we check our units, molar will cancel with molar, and it'll leave us with minutes, but minutes actually on the bottom of a fraction. Do you see that? The unit for this happens to be per minute in this case. That's a weird unit. That's okay. That's what the unit has to be. 1.5 minutes to the negative 1. That's a counterintuitive unit, but that's okay.
1.5 per minute?
That's right.
1.5
1.5 per minute. Nothing per minute. Just think of hertz. Hertz is just per second. That's all hertz means.
Wow.
Hertz means whatever you're talking about happens per second. 60 hertz is whatever you're doing happens 60 times a second.
Okay.
You make it so confusing when you change your m's. You did a double like capital M and then like a lowercase m and then like
Moles and
how does
minutes.
lowercase m cancel with capital case M?
Those are all capitals.
Okay, what and
Big
what's the
M.
last one?
No, K is
Big M.
Not the M.
Oh, that's a 1. Okay, that's a 1. That's a big M.
And that's the big M.
There you go.
Cancels with the big M.
There you go.
Thank you
You are
for
welcome.
the confusion.
Got your back. So if you want to solve for k, you just substitute in and solve. Not so bad, right?
So K is whatever's happening per minute. Or
That's right. And to be honest, with these k's, the units are just going to be whatever they cancel out to be. The units will be weird. All right? The units are going to be all over the damn place. Rate constants have random units depending on what type of order they are. You can actually look at the unit, and that alone will tell you what rate they are. But does that make sense? In first order, if you change one thing,
the other changes the same way.
the other changes the same way. All right.
I don't.
Now,
Mid -1.
what about a second order reaction?
Multiplied by
Well, a second order reaction, let's look at. In this case, we do the same thing. We set up our reaction, and I run it for the first time, and lo and behold, just like the last time when I run this one for the first time, what's the rate?
A equals 1.5, 0.
I start with the concentration of 0.1, and the rate is?
0.15 molar.
Very good. But then this time, I go to double the rate, and what happens?
quadruple the rate.
It gets 4
You
times.
double A and then you quadruple the rate.
That's right. And then look what happens here. What did I do this time? I made it 4 times bigger. And what happened when I made the concentration 4 times bigger?
16
Is that 16? Yeah. Yeah, it is. Wow, good eye. So let me ask you this then. Changing one thing by 2 changes the other thing by 4. Changing one thing by 4 changes the other thing by 16. What's the relationship there? Very good, which is why we call them second order. In this case,
This one would be exponential.
when we multiply the rate by a number, crap. See, that's why I need my cheat sheet, which I didn't get to print because I had to cover a tech class and then break up a fight. That seemed like a friendly, funny fight. I still had
Should
to,
let them stop their own guys.
I'll keep that in mind for next time. When we multiply the concentration by a number, the rate goes by the square of that number. We will talk a little bit about why a reaction might grow at this, but it all has to do with geometry. Reactions that can only collide in one very specific orientation will tend to exhibit first order reaction kinetics, whereas reactions that any kind of collision geometry will work tend to exhibit second order geometry. Which, if you think about it, makes sense because you're operating in a two-dimensional plane in the one case and a three-dimensional plane of collision in the other.
How can you have a two-dimensional plane of collision?
In other words, they have to be lined up before they can collide.
It's kind of like
And
inside
everything has to be lined up before they can collide?
No, like they have to be not only aligned in motion, but also aligned in orientation. Right? Think about coupling a train to a train. Do you ever have an electric train set when you were a kid? Right? If you want them to couple, you have to run to it this way. And if you T-bone the other thing, are they going to stick to each other and then be one train? No, you're just going to knock the other one off the track. They have to be aligned orientation-wise. Or if you put them backwards, they repel. For an atom, there is no orientation. But for a compound, I mean, let's take the simplest possible thing. If the collision had to happen so that oxygen hits something, then it has to be the oxygen that hits, not the hydrogen side. And if the hydrogen side hits, the reaction just doesn't happen. That's a very simple example of a geometrically limiting one. Yeah?
So for this, with the equation delta A using the variable of A, delta A to the power of 2
Yep.
is equal to rate.
Yep, and there's still going to be a K value. We're still going to have some constant, and that constant will always depend on what the reaction is, what the temperature is, what the pressure is. So that K value will always change based on those things. But
does it make you somewhat uncomfortable that your second order reaction is EG3?
nope, no, I'm fine with that. So now, how could we solve for this K if we wanted to?
Oh.
If I wanted to solve for K here, what could I do?
Why would it be EG3?
It's second order.
Square root. First order is 2. Zero order. Divide under first and square.
Well, yeah, I think we could just say K is going to be equal to the rate divided by
A squared.
concentration of A squared. So there we go. Do we have an example that we can use? I mean, we have 3 examples we can use. Which one do you want to use? You want to use 0.4? All right, cool. We can do that. What numbers would I put in here? If I want to solve for K,
On the bottom for A squared is 0.4.
0.4 squared. And what's the unit on that, of course? Molar squared. And on the top, we would have?
2.4 molar per minute.
Okay.
So you don't have to.
And somebody do that on the calculator. 0.4 squared is 0.16. 2.40 divided by 0.16 is going to be on the order of 10 times bigger than that. So we're going to be hitting around 20. This number should be around 20.
Why don't you be wildly off?
Sometimes I'm wildly off. Other times, I'm not. Let's see what happens. 15? I can live with that. 15 even? Perfect. And what would our unit be here?
Molars cancel out, so is it?
Does molar cancel out?
No, it's molar unit.
Because on the bottom, how many molars do we have?
Here, so it's.
So careful. So minutes is going to be on the bottom. The molar on the top is gone. one of the molar on the bottom is gone. So the unit will be molar on the bottom and minutes on the bottom. That's an awful unit, but there we go.
Yeah, because your minus is
I know.
Is that -1? Does that -1 mean per without having to?
Yeah, it means on the bottom of a fraction. It also, you can read it as per. It means division. A negative exponent means that instead of multiplying by that, you are dividing by it. So you're dividing by it one time. Dividing by it one time. There you go.
So it's kind of like that looks like momentum, so kilogram per
Love it.
kilogram.
Yeah, and worth noting, K-value units are ugly.
Why do you have to square it on the bottom?
Because the equation is second order, which means that in these equations, the concentration is always squared. That's what we saw here, that doubling concentration doesn't double the rate because this relationship is such that when you double it, we get 4 times, which means that whatever you're doing to the concentration, it is being squared.
On the rate, not the concentration.
Oh, no. I was going to add the word ugly.
The rate is being squared by the concentration, not the concentration being squared.
Well, say what you just said again so I can respond.
The rate
Logically.
isn't being... Okay, now you got me confused.
Yeah, you
The rate isn't being squared, the rate... Oh my god! See, I can't speak now.
That's okay. Can I try to explain it? So what we're saying is when we want to find the rate, we're saying that the rate depends on the concentration. And so because it depends on each other, that means there is some mathematical relationship where we can say rate and concentration, and there's something we can do here to make those equal. In other words, there's some way that changing this changes that. There's a mathematical relationship there. And then when we looked here, we saw that if I replace this number with a number that's twice as big, this number gets 4 times bigger. Well, that isn't just simple multiplication then. That is an exponential relationship. And then I know that it's not as simple as 1 to 1. 0.1 doesn't become 0.1. 0.2 doesn't become 0.4. So there's some number in front here that is changing that in a linear fashion as well. There's a constant.
Okay, and then with your units on the bottom, which is the most confusing thing I've seen, say m -1 and min -1.
Yeah, so what we have here when we go to solve this is if we were to do this slowly, we would have 2.4 molar per minute, which is the unit here, equals K times 0.4 molar squared. Okay, bear with me here. So let's do this. We have 2.4 molar. And I'm going to put minutes on the bottom of this fraction so we can really see it like that, right? Equals K times, and then 0.4 squared is 0.16 molar squared. Does that make sense? Okay, let's solve for K. I squared both things. 0.4 squared is 0.16. Molar squared is molar squared. Now, when I go to solve this for K, I'm going to divide this by 0.16 molar squared. But then I have to do the same here, which would give me K being equal to 2.4 molar over 1 minute times 0.16 molar squared. And now if we look here, that 1 obviously just divides away. The numbers divide to give us 15, we said. And then if we look at units, this molar can't cancel with this molar because there's 2 of them, but it cancels away the squaredness of it. And we're left with 15 over minutes times molar. And you could write it that way. You could say K equals 15 over minutes molar, but that's clunky. So instead we say K equals 15 minutes to the -1, which means you're dividing by that, times molar to the -1, which means you're dividing by that.
The -1 just means it's under a
Per.
fraction.
In other words, 15 per minute molar. You'll get used to it. Okay, there are relationships that are higher than second order, but they're beyond the scope of this course. In fact, they're beyond the scope of my understanding, so we're just going to move right along. I mean, mathematically they're simple. You would just, instead of squaring, you would cube. But I don't know what they would look like.
Probably very similar.
So a rate law then is an equation that defines the rate of a reaction in terms of the concentrations. And for reactions with only one reactant, it will always be rate is equal to some constant K times the concentration of your reactant to some exponent.
So is this true for like decomposition reactions? Would that be the correct?
And you need to do an experiment. Sorry, I will answer your question. I just don't want to lose my train of thought, which, as you know, I do. You need to do an experiment like above to figure out which exponent goes here. These are derived experimentally. So if you did an experiment where you changed the concentration of A 3 times and redid the reaction, but the rate never changed, then you would know that M must be. The rate never changes. No matter what you do to A, the rate just never changes.
Zero.
That's got to be 0, in which case you could just ignore this, right? If you doubled A and the rate got twice as fast, and then you tripled A and the rate got 3 times as fast, and you quadrupled A and the rate got 4 times as fast, then you'd know this exponent must be 1. Beautiful. And if you doubled A, but it didn't get twice as fast, it got 4 times as fast, you'd know that has to be a squared relationship. So you have to do an experiment to figure M out.
Is this law only true for, like, I suppose this looks like a decomposition reaction? Would it also be true for stuff like synthesis and displacement, or specific?
They would all follow a rate law, and you would have to experimentally determine what the rate law is. And this is constant for a given reaction at a given temperature and pressure. And if it were gases, you could throw volume in there to mix, but you get the idea. If you change the temperature of a reaction, it's going to change. We'll talk about that tomorrow. If you change the pressure on a reaction system, it will change. But if you keep all that constant, then it will obey this law with that as a constant value. And you can look up the K values of different reactions online. Now I know what you're all saying.
No.
I know what you're all thinking.
I'm thinking.
I know what you're thinking.
Confusion.
You're thinking, but Orlando, how often do we do a reaction that only has one reactant? That's what Elizabeth's thinking. Elizabeth says, Orlando, this is both mathematically unsatisfying and intellectually unsatisfying to my budding understanding of chemistry, because I know that most reactions don't have one reactant. Most of them have at least two. In fact, outside of decomposition reactions or hydrolysis reactions, pretty much everything has at least 2 reactants, right? So, how would you approach this if there's 2? And the answer is the exact same way. It's really not any harder. It's just instead of having one concentration with an exponent, you're going to have 2 of them. And it's not so bad.
And that's 2 tables? Or is that
No, it's 1 table. So can we take a look? Let's do an example. Let's look at this, and I've put a spoiler in the example title, which I debated with myself about, but whatever. Spoiler alert. Let's look at 2 reactants where one is going to be, and the second one is going to be. Let's see if we can figure out which is which. So here, this is the experiment we do to figure out our relationship. So I'm going to make a note about this. You would design a simple experiment to find the order of each reaction. To find the order for each reactant. Because it is possible that only one of your reactants affects the rate. In fact, that's what we're going to find here. One of these reactants changes the rate of this reaction, and the other one does not. Interesting. So let's take a look here. In this case, you'll note when I did the first trial, how did I set it up? The first time I went to do this, I took my A and I mixed it, and what concentration did I mix A to?
0.1 molar.
Great, and I took B and I mixed it, and what concentration did I mix it to?
1 molar.
Great, when I put them together, what was the rate of the reaction?
0.15 molar.
Awesome. Then I threw all that away. I put it in the waste beaker, cleaned my glassware, probably got fresh glassware because I'm a high school student, so I just, use as much glassware as humanly possible. Actually, you guys are pretty good. Man, my last 4U chem class was deadly. They never saw a beaker where there weren't I could use 6 of these in this lab and just make a huge mess and then leave them sitting out. So they set it all up again, and this time, the only thing they change is, did they change B? Why would they only change one thing at a time? That's right. If you change 2 things, then you don't know which thing caused the effect, right? So they keep this the same, but they take this and they double it. And when they doubled A, what did they find?
That the rate stayed the same.
Okay, so let's go with that. So that means the reaction is what order with regard to A? Is 0 order for the concentration of A. As we change the concentration of A, the reaction doesn't change. So we could say the rate is equal to some constant K, and then what, if we put concentration of A in, what exponent would we put on that? 0. And do I even need to write something to the 0th exponent? So really, that, when we finalize this thing, is going to go, because it just doesn't matter. Anything to the exponent 0 is just 1. That does not matter. But let's keep going, because there is something we can do that does make a difference. If, on the other hand, I keep A the same, that just says same, but this time, what have I done to 2? To B. And when I doubled B, what happened?
The rate changed
And how did it change?
by double.
Very good, it doubled. So doubling leads to doubling. They are color code. That's purple and pink. Oh, you can't really see that. Oh,
You always pick the
oh I'm sorry.
That looks like the same dark red.
Well, am I lying? See, I'm telling the truth. I'm sorry. Okay, the board doesn't suck. I think I have the best projector of any classroom in the school, but it's not perfect. Nothing's perfect.
That was all color coded, and now I can't erase it because I did.
You'll be all right. You're tough. There we go. So the reaction is what order with regards to B? Very good. And so we can keep going in our equation. We can say it's also multiplied by
The concentration of B power 1.
to the exponent of 1. And in that case, we would say rate equals K times the concentration of B to the exponent 1. We don't have to write about A. Do you guys mind if we don't do an example of solving for K here just because this is, well, actually, let's do it. You solve for K.
Exponent 1 just be the same as originally?
Yeah, this ends up being exactly like this.
X times itself.
You do not need to write the 1. That's a great question. Do we need to write an exponent of 1? No. You can just write that. In fact, that's a better answer. And if I wanted to solve for K, what would K equal?
Divide K out under rate.
Yeah.
Oh, you're trying to find K, sorry. Divide.
To solve for K, you're right. I wouldn't divide the K out. I would divide...
Concentration. Sorry.
Yeah, so I would do rate divided by
Concentration.
concentration of B. And in this case, I could use any example I wanted.
So then it'd be, this one would be just
We could use A.
per minute for K.
Yep, and it would just be 0.15 molar per minute in 0.1 minutes. And that, if I'm not mistaken, should be 1.5. And it would be minute to the negative 1. Sorry?
Is it minute? Don't the minutes cancel out?
But that shouldn't be minutes down there as
That should be
Elizabeth is very quietly trying to politely be like, Orlando, wouldn't it, aren't you, is it possible you're stupid? Might you be the dumbest person in this room right now? It was like when I go out for dinner with my mother. To this day, if I order something expensive, she kicks me under the table. It's just like an instinctive reaction. She can't help herself.
Does she realize afterwards?
Afterwards, I think she's like, yeah, that's right. Take that. But yeah, because when we were kids, we never had much money. So if we were eating out, it was like a treat. But it was like, this is not the time to like order something fancy on the menu. Or like if I get a refill of my drink, and I'm like, Mom, it's not the 80s anymore. Refills are free. Oh, shin kick, baby. Bam.
I'm in my 30s. You can't be kicking me anymore.
As my mother has often said, and I'm sure somebody else in this room's mother says this, I brought you into this world, and I'll take you out of it. Does everyone's mom say that? I know my mom says that.
To be honest, I was just a perfect child.
Well, there you go. See, I like that, yeah.
My father says
My mom says that a little too often, so.
Yeah, there's always the concern when you start to think, does she mean this? Is she seriously threatening me with death here?
just threaten them back. Simple solution.
I just make fun of my mom's people.
The guy you brought you into the world.
Yeah. We just thought it was something
I'm
weird.
more Ashdod.
Do you know, I distinctly remember the first time I ever taught this lesson, I'm just remembering this now, was at school where we had a lockdown drill, and we had to turn all the lights out, so I turned the projector off, and we just get huddled in a circle, because it was a small class, and quietly kept doing the lesson on a desk. I distinctly remember that. Yeah, because I didn't want to lose the day. No, sorry, I've got it wrong. Oh, it's so much better than that. It wasn't a lockdown, it was a fire drill.
Oh,
And it wasn't a planned one. It was somebody pulled the alarm.
Oh, my.
So I took I had this big-ish whiteboard that sat on easel that I sometimes used, and I took it out in the field and I made them sit and listen while I kept teaching this lesson in the field. That's right.
This man.
I love that story. I don't know why I got it wrong.
Did they care at all for it? Were they listening?
Oh, they're great. And there are like 32 kids in that class. That's right. That was a big one. That was South Lincoln High School. Oh, I remember that.
I need a big class and a small class.
Because I've had a lot of both. And South Lincoln had a lot of both. All right, let's take a look at this one, guys. In this case, now, if we pretend that we didn't see this, we avoid spoilers. If we look here, in every case, I want to keep something the same and change something. God willing, if we design the experiment nicely. So what did I do here?
Double.
I doubled it. And when I doubled it, what happened to the rate?
It doubled.
It doubled. So what can you tell me about the reaction with regards to B? Or to A, rather.
It looks like a first order.
Yeah. So the reaction is first order for A. If we want to start writing the equation, what could I start saying?
K equals A.
K equals?
Yeah, K. Oh, rate equals, sorry.
Yeah, no worries.
Rate
I
equals
wasn't trying to give you a hard time. Rate equals K.
Concentration of A.
We actually write the word rate, so I don't know why I just put an R. Rate equals K.
It's the concentration of A, and you don't need to put exponent 1.
Very good. It's linear. And now let's look at a case where we keep something the same. So here, these are the same. But what did I do here?
Why did you erase
Double it.
I doubled it.
And nothing changed.
And did nothing change?
No, it doubled too.
Why is there a
Double.
thick blackout?
Because it's a spoiler. It says what the rates are.
Okay, why don't
We
we
have
black it out
a paper that
ourselves?
we can read.
So what can we say here?
But we don't.
B is also first order.
The reaction is first order for B.
This is a...
And so if I wanted to put that information into my equation, what could I say?
Concentration of B, and you don't have to write it.
Very good. So look, for this one, we can just say no problem. The rate is some constant K times the concentration of A times the concentration of B, and there's no exponents because both ones have a first order effect. Doubling A doubles the rate. Doubling B doubles the rate.
What if you double both?
Then it would do 4 times the rate. Doubling and then doubling again. And if we wanted to solve for K here, easily done.
Rate over AB.
Yeah, we would just say,
Since you have A and B, would the units be a bit different?
yes, the units are going to be different. Very good.
I feel smart today.
I feel smarter than you did.
Stop! Stop it.
Okay, kids, don't fight.
Why not?
I ruining my mojo.
I already broke one fight up today.
Just don't break
It's my
yourself
limit.
up.
Come on, well, let's fight.
Okay, so listen, talk to me. What is the rate? What example do you want to use? Let's use easy numbers. I like easy numbers.
So 0.15 over, or 0.15 molar per minute over 0.1 times 0.1
0.1 molar times 0.1 molar. And I should mention actually that, well, anyway, don't worry about it. It's worth
What
keeping.
were you gonna mention?
Well, it's worth keeping in mind that if you put subscripts on these and said what molar you were talking about, could be interesting, but that's okay. We're not going to worry about that. And in this case, that's going to be 150, I believe. No, 15.
No, just pick one.
15, and that should just be minutes molar -1, right? Cool. And again, the K value is easy to solve for, and in theory, any one of these should give you the exact same K value. In practice, they might vary different a little bit. So if you wanted to get a hyper-accurate K value, you might do it with all of them and take the average in real experimental data. Is this real experimental data? No, I just made these up. Made them up real good. Okay, now we're just going to do one more example. And in this case, one is first order, one is second order. I want you guys to write the rate law for this. Take 3 minutes, go through. You tell me the rate law. You're going to tell me rate equals, there'll be some K, and then wah, 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 wah. Wah, 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 wah.
Are you trying to be one of the adults from the Peanuts?
I love Charlie Brown, but kind of, yeah. I'm doing an impression of what I hear every time they page me into this room. It was hyper humiliating. I forgot about my coverage today. And they paged in to tell me, and I had to ask them like 11 times what they were saying. Until finally she was like half shouting, spelling it out incredibly slowly, and then I felt pretty stupid.
Is this the true story?
Yeah, yes, of course.
Well, I heard them call you to the office.
They got so frustrated they didn't even tell me, like, come to the office.
Well, I was in the other room, so I heard that, then I paged it. It was a whole thing. It was a real thing.
Oh, I thought it was a fake.
Yeah.
Like, pigeons, because they're all birds. They're not birds.
Birds aren't real.
What?
She birds.
Birds aren't real.
Prove it.
They're drones!
The drones and have been since the 70s, I believe. Is that the guy's thing?
Yeah.
Yeah.
They take my 2 birds and I charge them.
Yeah, and they go on like electric poles, that's how they charge.
Is
They have a
that,
little,
know that
they
part?
have a little wireless
did
thing
not.
that
is
plugs
that,
into.
is that the idea?
Yeah, like
amazing.
if by them going on like the.
That's why they go on electrical ones. I
Yeah.
hadn't caught that part. That's really funny.
That's how they charge.
What I know is that in like cities that had like anti-mask rallies, he would go and just surround the anti-mask rallies and have birds aren't real rallies. And then there was one, you know, the Westboro Baptist Church.
Yeah.
These are these people who like, it's horrific. It's truly horrific. But like picket like military funerals and picket like funerals of gay people and hold horrific signs that says horrific things. Well, the birds aren't real guy has started just surrounding them with many more people chanting birds aren't real. And I kind of like that. Anyway.
What, is he serious though?
No, that's the point. He is. His story.
Oh, okay, thank God.
His story is like when he was in university one day, there was a very serious rally happening in town, and then there were a bunch of counter protesters, and he thought, wouldn't it be fun if one of these people who was in there was just like secretly protesting something really silly, and he came up and he just got a piece of paper and wrote the first thing that came to his mind, which was birds aren't real.
You know what you
And he just
reminded
stood
me
out there and started chanting it, and then the news came and asked him what he was talking about. And so he just started spitballing on the spot about drones in the 70s, and the government's replaced them, and
Sir,
it became a thing.
You know what you just reminded me of? I remember watching some videos online, and there were like big protests and riots in
Yeah.
like Washington. I can't tell you when,
Yeah.
but there are counter protests and protesters going around, and there's this one guy who's going from protest to protest, trying to give everyone Pepsi.
I like it. And they were just like, I prefer Coke.
Yeah, and
We can all listen. You're
That was an ad.
you're pro-Nazi. I'm anti-Nazi, but we can all agree on one thing, which is that Pepsi's just too sweet.
It's kind of close.
It's too sweet. It's just too.
Pepsi's the better of the two.
Disagree. Too much
I
sugar
fully
content.
agree
Anyway,
with that.
different
Yeah,
discussion.
because it's your point. No doubt you agree with it. I would be really confused if you didn't agree with your own point.
Okay. Anyway,
Coke is
That's happened before.
talk to me, guys. What is this rate law?
R or rate
Yep.
equals K.
Yep.
Concentration of A
Yep.
squared,
Okay.
and then times concentration of B.
And that's not squared.
Yeah.
Okay. Do we agree with that? We like that? Okay. How'd you get that?
40 hours.
Let me try and remember. Okay, so look at A.
Yeah, I'm looking at A.
So from 1 to 2 it doubles, but on the right, from 15 to 60 it quadruples. So that just by looking at that, I can already tell it's squared.
Okay. So I doubled it here.
Yeah.
And when I doubled it here, it got bigger by 4 times. And just to be safe, yeah, that's the same. That didn't change, right? That was no change there. Okay, cool. So that's how we know that that's a 2. How do you know that there's no exponent there? I mean, I know that the question says one's first order, but how do you know I'm not lying? I lie. Sometimes I lie about what number a lesson is.
Because from like point 1 to point 2.
I burped.
Let the Shanta go.
Go, Chishante.
Can't be like my-
Very good. So that means that has to be first order. Very good. And if we wanted to, could we solve for K?
Yeah.
Yeah, trivial, right? To solve for K,
You ain't got none.
we would say K is equal to what?
House.
The rate divided by...
A or concentration of A squared times concentration of B.
Very good.
And then our units are going to be weird for this one too.
I'm the
Yeah,
super your mom.
units are going to suck, but that's okay. Guys, could you focus here, please? We could use any example we want. I don't know, I'm going to use this one. So my calculation then would be what? What goes on the top here?
It's, 1.2 molar.
Yeah.
Right.
Molar per minute, yeah.
And then A is, so that's what, 0.4?
Yeah, I'm going to put in the 0.2 molar squared
And then molar squared.
and then 0.2 molar not squared.
Yeah.
And so K is going to be equal to, well, right here, 0.2 squared is 0.04. Squared again is 0.008. And so this is going to be a pretty big number. That's my hot take. Big number. Somebody tell me what the big number is. 150. There we go. And let's talk units. Molar is going to cancel with one of the molars, leaving us with molars squared on the bottom. And we also have on the bottom
Minutes.
minutes. So we would have minutes to the -1, molar to the -2.
So when it's on the bottom and it's squared, you put -2.
That's right. Negative means on the bottom, and 2 still means squared.
So if it were cubed, it'd be -3.
Very good. Yep. And there we go. Now, note, the overall reaction rate is a term you'll see sometimes, and that's just the sum of the exponents. So let's go calculate those in green here. The overall rate is the sum of the exponents.
Would you wait for me to get a green pen?
No. So in this case, what's the overall rate here? First, second, third, 0, what?
For example, 6, 0.15 plus.
No, overall order. Just the overall order. Well, we have a 2 here, and what's the exponent here?
0?
No,
1.
1. So the overall order is?
You didn't write it at all, so you said
That's right. When we don't see an exponent, the exponent is?
1.
1.
But you said you wouldn't write it for 0 either. That's why I was confused.
If it's 0, it's
Zero.
nothing. Is it not?
But they're different. If I did it for 0, I wouldn't write that at all.
Yeah.
It just wouldn't be there.
Oh, okay.
Yep. So overall, the order is third order. Good.
Oh, that's
What's the overall order here?
2. Second order.
Right? An exponent of 1 and an exponent of 1. So overall, that's a second order. In other words, if you doubled everything here, things would quadruple.
So then be a 4th.
Whereas if you doubled everything here, it would actually go 8 times faster. So that's the overall order. The idea with overall order is what if you doubled everything?
Is there
What if you
such a
tripled
thing as
everything?
a 5th order
Yep.
reaction?
Yeah, sure. What's the overall order here?
1.
If I'm understanding this correctly, the maximum is 6th order, yes?
On the basis of what we've done, yeah, that's correct. But keep in mind that could a reaction have 7 reactants?
I mean, yeah.
Yeah, could.
Well, no.
Reasonable?
Sure.
Well, what is one of those reactants going to react with?
You can get some very complicated organic reactions. And yes, they happen in steps, but it would not be remotely hard to imagine. That just means a recipe that has 7 ingredients, essentially. Okay.
Right order? Like, is order supposed to be in there?
Yeah.
And this is A plus B yield C for this kind of reaction.
That's right.
Okay.
And you'll note, what doesn't it depend on? This is... The rate of this reaction does not depend on the concentration of the products. Which makes sense, because do the products have to bump into each other for the reaction to happen?
No.
No, the reactants have to bump into each other.
The rate of this reaction? does
Yes.
depend?
Yep, sorry.
So then, what?
By the way, is that a lie? Oh, it's such a lie. But it's a reasonable one. It's technically correct, though misleading. The rate of this reaction
Wait,
doesn't
you said
depend on the
freaking
product.
word. Technically.
Exactly, and as I've always stated, technically is the thing people say when they are saying something that is not actually very true.
Well,
No,
you
you
accept
said
that
that's
it's
not
something
true.
they say when they say
Wow, you're really going overboard on that start.
So, Mr. Orlando,
Like it's just erase and start over.
could we graph this?
That's
Right?
Would we be able to graph this?
Oh, you sure?
And then
That's
if
good.
that's the case, would these ones be exponential?
Well, yes,
enough with you and your graphs.
and in fact, you will. I'll make you one better. You could graph this, and you would get a 3-dimensional plot. Oh, sure, you have an x, a y, and a z. Yeah. For anything with 3 reactions, you can make a 3-dimensional plot. Yeah. Yeah.
An exponential 3-dimensional plot?
Yeah.
I've never seen that.
Well, not exponential. No,
That's still linear.
that's parabolic.
Oh, you're right.
Yeah, if you look, that's linear. This is, we didn't mention it, but this is
That's linear 2D.
this is a parabolic relationship.
Not me. That one's parabolic. That one's linear.
This is linear. This is flat,
And Mr. Orlando,
linear with no slope. Yep.
can you shuffle properly?
Not great. I can, but not great.
No one else here shuffle
I'm
properly?
weak. Okay, guys, there's homework here, but the last thing I want to do today is I want to do this example here. Here's a fun reaction. Xenon gas reacts with fluorine. Hey, what's xenon?
Isn't that, we've talked about this.
It's a noble gas. I thought noble gases didn't like to react. Well, sometimes you can make them. In this case, fluorine is so reactive that it will actually react with a noble gas. It'll steal some electrons.
Refresh my memory, xenon or noble gases are stable.
Yeah, that's right. Which is why this doesn't need a 2 or a 3 here. It's just good old-fashioned xenon atoms floating around.
That's why there aren't two. 'Cause I was going to say, would they be considered?
Yeah, not diatomic because they're stable on their own. Okay, guys, I want you to do this and listen. Listen, look here. This reaction, they haven't laid the table out very nicely.
Too choppy.
You know, like if I were doing this, I would just, the first time out, keep this the same, double that, right? Did they make it easy on you?
No.
No, in fact, can I say something?
Don't do that.
This experimenter sucks. And they're trying to make you look stupid.
What?
Don't let them make you feel dumb. Get this.
Better than this?
I like that.
Still choppy.
Brady, I feel like I need to sit next to you more often. I feel like there's probably always really nice little drawings, and I don't always get to see them.
That's how you do this.
My jack.
Actually,
It's my jack that I was using. I wanted to use this jack. I was
Hey, guys, what I'd like you to do is this question, so shut up and do it. Thank you. Sit down. No, give me the deck. Come here. Hand it over.
Guess
Thank you.
that's how
This is why you
Get to work.
Why?
Shh.
You do realize you're the one that made a huge deal about everything else. You do.
Try.
Why don't you stop being toddlers and do the bloody reaction?
Reaction for
Instead
what?
of playing Fortnite on
Video
your
games.
phones.
As I say so often, I'm with Caleb on this one.
What, play video games on your phone instead of arguing like
That's right. I would much rather you quietly play video games than be a noisy distraction. I would even more rather you attentively do the question, but you know, it's your grade. But Caleb is never disruptive when it's work time. Yeah, let's just say I would be fired by any casino. You gotta be able to do it so that they don't show it all, right?
Well, I don't know how you guys do the merch thing. I've never made it.
Like, well, it's easy to do if you can lift them up, right? Like, then you just,
Yeah, I can do that one.
oh, that was weak. But yeah, but again, you can't do that because,
You're not allowed to take them off.
yeah, they need to be unexposed at all times, right? So
Is
it's
that
gotta be.
cool?
Well, of
Yeah.
course, yeah.
It's not allowed to come
You
off.
can't have people looking. No, a casino dealer is highly trained, and they are under the gun because they're on camera all the time, and it's money for the casino, right? Like they are. We used to sneak into the training room in the casino because I managed a restaurant that rented space in the casino, and you go through the back, like through shipping and receiving, and like there's a room with all dumpsters and all this stuff in the back, and all of a sudden you open this room, and it's dingy concrete like everything else, only there's like the velvet tables and like all these like swanky fancy like dealers tables and couches and chairs, but otherwise you're just in this weird concrete basement. And so yeah, we used to go down after shift at like 3 a.m. and play cards in the training room. And then every once in a while somebody from the casino would come and be like, what are you doing here? I'd be like, playing poker, do you want to join us? And then usually they would not.
And then they kick you out.
No, you know, they never did. They're very nice. I got along very well with the casino people.
Was there ever times when they did play with you?
I think they probably weren't allowed. I think usually they would just pretend they hadn't seen us and go about their merry way. They had like dealers have a good paying job though, so they don't want to lose it. You don't want to. The last thing you want to do is get fired for something stupid. Like the valet, we accidentally got fired.
Accidentally.
do.
You have valet fired.
So we used to have to pay for parking, and it was a lot. It could be like $25 a day for parking, and I'm not made of $25 a day. So I made a deal with some of the valets where they would bring us parking passes, and we would give them chicken wings. It's a good deal, right? So this was a pretty good deal. They'd bring us parking passes. Only we discovered that one of my idiot bartenders wasn't just using them to go park. He was getting valet service every day. So he was like pulling up to work, giving the guy his keys and just walking off. And when the supervisor at the casino found out about it, he flipped his lid and fired one of the guys. And I felt awful. It was bad.
Did
was
you
not
still keep
good.
your chicken wing deal though?
Yeah, well, there were like 4 more of them. Yeah. Anyway, the important thing is I felt awful.
And you kept doing.
I didn't feel awful about getting parking passes. I felt awful that we got this guy in trouble because one of my bartenders was dumb.
You should have fired the bartender.
He didn't do anything wrong at my job. He just, right? Like that guy got fired because he was doing something wrong at his job. Owen wasn't doing something wrong at my work. He was just an idiot.
Do you have a permanent black marker?
A what?
A permanent black marker?
Yes, I have all the Sharpies you could possibly want. If you go in the back prep room, there's a blue bin and those fine tip Sharpies, and then under that are the the bigger Sharpies. You can use whatever you want. They're all yours. Okay, guys, talk to me. What's this rate law?
I hate this one.
Yeah, the numbers aren't nice, are they?
Don't like it.
So listen, let's try this one. All right, we got 8 minutes. We can do it. What is a nice pairing where I only change one thing? If I look at this, that looks like it's been kept the same, right?
Yeah.
So that's good. In that same one, what did they multiply by here?
3, 4.
3.
No.
Well, if we're in doubt, let's just divide. Because the opposite of multiplying is dividing, right?
3.
It is 3, but that's okay. It's okay to be confused. Let's talk. So look, if we did 1.5 divided by 0.5, we would get 3. So sure enough, that's been tripled. Now, in the same span, what happened here? Well, I don't know. Let's divide. So same thing. We can do 0.01406 divided by, what was the original one? 0.00156.
Oh wait, Mr. Orlando, number 2's.
And, what did it basically work out to be? 9. So what is the order with respect to xenon? When I triple it, it gets 9 times faster.
That would be
Squared.
Very good. So that's squared. So it's second order for the concentration of xenon.
Oh, so okay, so I can look for ones that haven't been changed drastically, and I can just use those ones instead.
So the rate is some constant K times the concentration of xenon squared. Now we need to find another one. Now we need to find one where we don't change xenon. And there's not a bunch of great options here, but I've got these ones, right? That's unchanged, right?
Yeah.
And in the same span here, what do we multiply by?
There's one in fluorine where it doesn't change. 1 and 1.
But we've already got fluorine not changing. Right? We already did 0.25 and 0.25.
God, Will.
Right? We already locked fluorine in.
We did?
Yeah, here. Look, when we did this one, we did 0.25 and 0.25. So we choose an example where fluorine didn't change. But now we need an example where fluorine does change. And what does fluorine change by here from 1/4 to 1.0? Nope. 4 times, good. And what happens here? Can you do that in your head?
Oh my god, kill him.
I can't do that in my head. Oh, for the love of God. Stop.
You oil that thing.
I think it just came from a tech lab. Maybe they could have oiled it. 0.00625. And what should I divide it by?
0.00156.
0.00156. And when we do that, we get 4. So making it 4 times bigger makes it go 4 times faster.
So that's first order.
So it's first order
Why did the X after?
for F2. And so how would I finish my rate law here? F2. And should there be an exponent there? No.
You could, but
There we go. Now, can I solve for K?
yeah, divide your constitutions into 8.
Yeah, we solved for K. And so we would get K is equal to the rate divided by the concentration of xenon squared times the concentration of fluorine. Do we care what example we use? They all suck.
The first one.
First one it is.
The numbers.
Actually, this one I didn't. This one I stole from a textbook, shamelessly. So what's the rate in this first one?
For xenon, 0.5. Oh, the rate. 0.00156.
And that's molar per second.
Is it? Yeah.
Yep. And then, what's the concentration of xenon here?
0.5 molar.
Yeah, and we have to make sure we do what with that? And what's the concentration of fluorine? 0.25 molar. And is that squared?
No.
Okay, maybe you can do that in your head, in which case, good for you. But you know what I can't do? That in my head. So I'm going to type it in. I'm going to say 0.00156 divided by, and if I'm going to use a calculator, I got to make sure it's in brackets, 0.50 squared times 0.25, and that should equal 0.02496. And what will the unit be? Well, that molar will cancel with that molar.
Molar squared per second.
Both per, though. Per second, per molar squared.
Why does second go first? Is it because it's on?
Whatever. If you want to do molar squared and then second squared, that's fine. Or second. That's an S.
Second.
Because
it's
we're in
not minutes
seconds.
anymore.
Yeah, we're not in minutes on this one. And so if we wanted to rewrite the rate law, we could say rate equals 0.02496 seconds per second per molar
Squared.
times xenon squared,
Molar squared.
of course, which it always was. Try to pay more attention, Will.
Sorry. Jeez.
Not sorry enough. Anyway, there we go.
Sassed all week.
There you
Oh, yeah,
go.
that's true. You've been sassy.
I've been getting sassed all week.
I know, I like it.
Wow, okay, now we're going there again. You're racist. No, we're not.
No, that would be terrorist.
Moving on.
Isn't hair color a sign of race in certain cases?
This conversation can't go well.
What?
What do we say we just don't have this conversation right now? How would everyone feel about that? I'd feel pretty good about it, actually.
I do too. I have strong feelings about my.
About your people. May I ask, like, what is your ethnic heritage?
My ethnic.
Yeah.
Yeah, but it's been too diluted.
No, but like I don't know what Novak is. Is Novak English? Is it?
Hungarian.
It's Hungarian.
So I'm
Okay.
like half English, like Britain.
Okay.
Half Hungarian. I don't know how percent, but a large percentage like proper French.
Oh, really?
Yeah, like
That's
France
cool.
and a little bit of indigenous.
That's cool. Like
Because,
Canadian indigenous.
Yeah, because
Very
my
cool.
my French ancestors have been here for like 400
He's a
years.
Frenchie.
That's really cool.
I find it cool.
Pierre Annabelle.
Yeah, that was almost my name.
Okay. Okay, guys, listen up. Look here. Oh, I'm sorry. Because I like to make sure that everything's lined up neatly so that I didn't do the thing where I go on crazy angles. Now listen, tomorrow will be nothing new. We'll do some work on this. Somebody sent me a request yesterday saying, could we go over doing some citations? So yes, we'll do that tomorrow as well.
I forgot the way you showed it.
Do you have a
for us last
calculator
night.
that you trust so we can redo that?
Yeah, grab me one of the, grab
Yeah,
me.
that's the problem.
We got one right here. All right, let's take a look. So,
I'm just curious where I went.
yeah, let's take a look. Because, well, this one we know. Sorry, one of them we knew.
We knew
This
that
one
this
we knew.
one
Yeah,
was
you
wrong.
just switched to sign. So let's look here. So, you never
Also, why did unit incorrectness
half for the mistake,
half.
a full mark for the answer.
but here it only got
1.5, half for
one
the
and a
mistake,
half.
one for the answer.
Is this 1.5? Yes, it is.
That's
okay.
That's 2.5.
That's
So let's see
2.5.
why I came up with that. Let's see. So, because maybe that should be 3.5. Let's see what we came up with. So, we said negative 46. Oh, you know what? And I took one off because, frankly, if you lay this out nicely, right? Because I taught you a formula for this, right, with the sum symbol and layout. So I want to encourage you.
Well, this
and
was-
listen.
This is organized fine. It's not
Well,
messy.
take this the wrong way. Don't take this the wrong way. But if it were organized fine, it probably would have led you to the right answers. So
Well, maybe it did.
Well, maybe, which is possible. So one of the things I say is that I never penalize people for bad form much if they get the right answer. And that's not much. That's not much. But I start getting... So anyway, so
That's
we'll
a
do...
quarter of the mark. That is much.
It's not that much. Could have done more.
Shouldn't have. I got the answer right. I don't see why a little
Well-
bit of form.
Well, because
Makes
the
it
reality
wrong.
of the matter is the world cares about form. Whether they should or not, they do. And
I
so
feel
I've got to
like more
tell you...
people care about the final answer than the form.
You'd be surprised. Anyway, Uh,
Fair enough.
and I'm not even saying for the record that that's the right thing, but it is the thing. So anyway, let's just quickly. Oh, I'm out of my equation. Minus the sum of n times delta H reactants. Okay, so let's take a look. So,
What does that even say? I have no clue.
not equal to what's above. So this is all good, and that just doesn't equal that. So you just made a calculator error.
Oh. You took 3
Wait,
marks
why
off
is
for
his
calculator error,
two-page
even if
where
I
mine
set
was
it up
one?
correctly?
Out of 10, yes. Yeah, that's correct. The answer matters.
Why is his 2-page? Mine is 1.
That's an assignment. This is
Oh,
the
it's
quiz.
different.
Things. Yep,
Okay.
different things. So let's take a look. So the first product is
product
NO2,
is
and let's just make
four
sure you got the right
NO2s.
number. Yep, which I think you did.
Yeah.
33.9, and you did 30. Yep, so we'd say 4.
Multiplied by 4 because
Yep.
there are 4 of them.
Yep, perfect. So 4 times. 4 times.
And I scratched out the ones that I
33.9,
wanted
and the unit on that
because-
was what? Kilojoules per mole? Kilojoules
yeah.
per mole. Yep.
KJ.
Okay. And then the next one we add is
This is.
yep, 6 times water, which is a liquid, a gas, and that's 241.8. Yep, good. Plus 6.
I didn't put like states because
Yeah, which
everything
is
here
fine.
a
Yep,
gas.
which is totally fine.
But everything is here is a gas, which means it would be
Yeah,
a
I'm
gas after. Actually, would it be a liquid or a gas after? Because it may gain some extra weight to it and make it a liquid, depending on the temperature.
Yeah, that is possible. You're totally right. But since we didn't say, we'll just assume.
Because since using oxygen, is it an exo? Or is that not a deciding factor? I don't remember.
That's not a deciding factor. I mean, it
Okay.
could be, but it's.
I thought that if you used oxygen, then it was an exo or something.
That will typically be the case, but that's not guaranteed. There could
Okay.
be cases where that's not true. So let's take a look there. So this is our setup, and I feel like we probably just switched a negative sign somewhere. So let's see. So we have 4 times 33.9.
-4.
Well,
Oh, on this side,
yeah,
on
I'm
this
just,
side,
I'm just
fair
gonna,
enough. Yeah,
I'm
yeah,
just gonna set it up.
Okay, you're doing one side at a
Plus
time.
6 times negative 241.8 minus 4 times
Okay.
negative
that's-
46.2.
Oh wait. Yeah. Okay. So I did. I'm like that's probably where I went.
Yeah.
wrong.
So I think, and the thing is, you knew that because if you look here, you said times -4, so you knew that you had to
Oh,
subtract.
I
that 'cause
just
it's a
didn't
reactant.
move that to the other side. So once again, I did minus that afterward. and
Yeah. So it's just
Oh,
a sign
wait, yeah.
issue.
No, that's not a problem because I subtracted this from this.
Yeah. If you had done what you said, if you had done what I think you're trying to say you wanted to do here, you'd have got it. But you.
No, I did it correctly because I subtracted this from this, which is the same thing as here.
Okay, but when you do that, you get 1130.4. So somewhere you added something when you should have subtracted, which is different by twice that. So you obviously added that instead of subtracting that. And like I think the reason is because like the truth is like you are adding it. But the problem is since these are both negative,
They're both negative?
well, since this is negative, like that's negative, that's positive, this should also be positive. So it should be that, which would give you 1130.4. One of these two got put in as a negative, and my instinct says it's that one.
Yeah.
Yeah. Well, we can find out. Because what was your answer? Your answer was
1500.
15. Is that 1515 or 1315?
1500 and that's 1315.2.
But is that
Which one are you pointing
like what
to?
is that? Is that
This
is
right
that the
here?
number that you rounded to that? I think so.
No, this number is this side.
Got it. Okay.
So that's not an actual pencil.
Yep. I see what you're saying. Yeah. Which means that was your error there because these are opposite signs. So that should have been 12. Like that should have been 1320. That should have been 1314.2.
Oh, so I was off by 1.
Yeah, so like that
so I
one.
may
That's
have misread that, but that
Yeah.
still doesn't
I
explain
think so,
this much of a difference.
well, it does actually because you end up having to double that mistake because instead of going,
Which is 2 at that point. If it's 1 off, then it's 2. which still doesn't.
So you probably did the same with that.
Explain
Yeah.
that
So I think you got the sign
So
wrong
I probably
on
did
both of them.
both of that and then the one difference.
Yeah. And in fact, since this is positive, I bet what you did is just miss that negative sign. That makes the most sense.
Perhaps.
So anyway, I'll call that 3.5. I'll up you by 1 there. That's closer than that. But I will say this, Caleb, your conceptual work is strong. If you're a little neater and a little more careful with following kind of layouts, you'll make fewer errors. And errors do matter.
Yeah.
Because like when you don't make little errors, your work is quite good because conceptually you're pretty strong. But setup
The problem
prevents us.
with this one is I don't typically use units at all in an equation until the very end.
I know,
where
but-
put my units on my answer.
Well, that's not how we do science.
So while I was writing it, I was writing
Yeah.
the units afterward because I realized I forgot them, and I just started writing KJ on everything.
Yeah,
'cause
which
I'm
is-
like, oh yeah, it's kilojoules.
which
for
is
everything.
totally